In the beginning, there was only darkness everywhere. Darkness and water. And the darkness gathered thick in places, crowding together, until at last, from one of the places, there came forth a man. Now the man brought from himself a rock, and he divided it into little pieces. Of these, he made stars, and he put them in the sky to light the darkness. Then, from himself,
the Mother of Water took pity on the bird's wanderings and crooked her knees to make a lap. The bird saw it and laid 6 golden eggs in the nest she made. All were beautiful in the making. Half one eggshell formed the earth itself. Its upper half arched the heavens over it. Its yolk made the golden sun. Its white became the moon. Its specklings were the stars. Its darker parts, the clouds.
At length, Ukko heard of Lindu's distress, and he resolved to help her. He ordered the winds to carry his weeping daughter to the sky. They lifted her gently and put her down in the blue firmament. There, Lindu dwells. Her white bridal veil spreads from one end of the sky to the other. Everyone who looks at the Milky Way sees Lindu's white bridal robes. She has forgotten her sorrow. At midnight, she waves her
Quetzalcoatl
hand.
was pulled to safety. The sky gods were so pleased with Quetzalcoatl, they made him the sun. Anansi became the moon, and the other captives became stars.
In the beginning, the sun and the moon were man and wife. The moon bore the sun many children, and they were called stars.
After
This family
a
did not
long
eat food
journey,
of the
they came to a round hole in the sky, glowing like fire. This, the raven said, was a star.
The cosmos. When ancient storytellers created these tales, they were trying to explain its mysteries. Though the mysteries they pondered were great, what they could see of the universe was comparatively small. With the unaided eye, man could see only the sun, the moon, 5 of the 9 planets, comets, and some 5,000 stars. In the early 1600s, Galileo, armed with an insatiable curiosity and a rudimentary telescope, opened the heavens wider to scientific examination than ever before. Today, some 400 years later, we know the universe to be inconceivably immense, so large that we've had to devise new numbers to describe it. And in man's unending quest to understand the universe, our ancient folk tales have given way to modern scientific theories. These theories, too, try to explain our universe. But where folk tales were accepted on the authority of the teller, scientific theories must be proven. Astronomers and astrophysicists use telescopes to observe the heavens in their continuing search for proof. But earthbound telescopes, from Galileo's simple instrument to our modern mountaintop observatories, are all hampered by Earth's turbulent atmosphere. So the best place for an observatory is in the heavens, out among the stars themselves. And NASA's space shuttle has given us the means to put one there. With an unobstructed view of the universe from its orbit some 350 miles above Earth, the Hubble Space Telescope will be the fulfillment of the astronomer's dream. The Space Telescope will see objects some 25 times fainter than can be seen using the largest telescope on Earth. and will distinguish details 10 to 30 times more clearly than is possible from the ground. The new observatory in space will produce images of unprecedented clarity. Images made possible not only because of the telescope's vantage point in space, but also because it is the finest optical telescope ever built. The Space Telescope's mirrors are the most perfect of their size ever made. Since the telescope is free of Earth's distorting atmosphere, optical scientists labored long and hard to create virtually perfect mirrors for the new telescope. Mirrors that will take advantage of the clear conditions in space. Mirrors that won't add distortion where there is none. The mirrors, of course, are just part of the picture. To make the most of the mirrors, the Space Telescope must keep them precisely aligned and hold them absolutely steady for hours at a time. So the mirrors are mounted in a strong but lightweight framework made out of graphite epoxy that will hold the telescope's optics stable as it orbits the Earth once every 96 minutes, moving from the blazing warmth of our celestial furnace, the sun, to the icy chill of night in space. Still, stable optics are useless if the entire telescope jitters in space. On Earth, we use the bedrock of a mountaintop to steady a telescope. But what steadies a telescope in zero gravity? The Space Telescope uses a sophisticated system to locate a target and hold steady on it, even though the telescope is continually moving as it orbits the Earth. Gyros provide a reference so that the telescope always knows its orientation. Star trackers and fine guidance sensors lock onto guide stars and use them to point the telescope at a target. With this system, the Space Telescope can remain locked on a target for hours at a time. The entire system is extremely precise, so precise that it's like being able to hold steady on a dime suspended over the Washington Monument from the top of New York's World Trade Center. The light collected and focused by the telescope's precise optical assembly is shared by several scientific instruments. The instruments use advanced light detectors and electronics to measure and record light, or separate it into its different components for analysis. All the instruments are mounted so that they can be easily changed on orbit, either for a replacement or a new instrument.
Straight back radio out from the telescope.
All the telescope's instruments and systems get their power from the sun. Space Telescope project engineer, Gene Oliver.
The Hubble Space Telescope is the most fantastic telescope ever built. It's not just good, it's the best. And it took the combined efforts of hundreds of scientists, engineers, and other professional people working as a team for many years to make it the best.
Once free of the confines of Earth, this precise scientific instrument will give astronomers a clear view, deeper into space than they've ever seen before. They'll actually be seeing back in time. Space Telescope principal investigator, Professor James Westphal.
It's because it takes time for light to go from one place to the other. As an example, it takes about 8 minutes for the light from the sun to get to the Earth. So we really are seeing the sun as it looked 8 minutes ago. If we look at Jupiter, it took 30 minutes for that light to get here. So we're really seeing Jupiter as though in the same way as it was 30 minutes ago, not as it is really right now. Oh, the North Star, for instance, takes about 50 years for the light to get here. So who knows what's happened to the North Star in the last 50 years. If we look at faraway galaxies, say a galaxy that takes 1 million years for the light to get here, we're really seeing the galaxy as it was 1 million years ago. And we even look at galaxies that are probably 1 billion years away. We're time traveling back in a sense to see those galaxies as they were 1 billion years ago. To look further back in time, we look deeper into space.
For example, looking at this quasar is seeing back 10 billion years, because its light takes that long to reach Earth. Let's follow the quasar's light as it travels over 10 billion years. When the light first began its intergalactic journey, our galaxy was nothing but a swirling cloud of cosmic dust and gas. While the quasar's light traveled for billions of years, this dust and gas coalesced to form the 100 billion stars of the Milky Way, including our sun and its satellites. As the light now reaches our solar system, life on Earth has evolved enough for man to orbit a space telescope above the atmosphere with sensitive instruments that can detect the light. What we see is a snapshot frozen in time, the image of the quasar as it existed 10 billion years ago.
Quasars continued to change. It's going away from us probably, and it's in fact likely that it doesn't even exist anymore now.
Clearly, a telescope is a time machine, using light to transport us into the past. Astronomers using the Space Telescope will be modern-day explorers venturing out in both space and time. Their quest is the same quest that has occupied man throughout the ages, to understand the mysteries of our origin, evolution, and ultimate fate. For modern astronomers, this understanding will be found in the refinement and proof of scientific theories. Theories like the Big Bang.
In the beginning, our universe arose from a compacted region of pure, exquisitely hot energy, billions of times smaller than a single atom. In the merest instant, an ultra-hot explosion brought space and time, matter and energy into being. The universe expanded and cooled. Primordial particles could clump together, forming the first atoms. Over billions of years, these building blocks of matter formed and reformed into the universe we see today. A universe inconceivably large and dark and sparsely populated with little islands of starlight.
But will this expansion continue forever? Or will the universe ultimately collapse back on itself? Space Telescope program scientist Dr. Ed Weiler.
We know the universe is expanding because no matter which direction we look at, we see galaxies moving away from us. We also know there's a lot of matter in this universe, galaxies, stars, planets, etc., which exerts a gravitational pull that's slowing this expansion down. What we don't know is whether there's enough matter or not to eventually stop this expansion so that it collapses someday, or whether this expansion will keep going on and on and on forever. To attempt to find an answer to this question, we need to do is plot the velocities of galaxies at further and further distances. To do that, we need mileposts in those galaxies, very bright mileposts, so that we can see them very far away. And what is a milepost? It's an object for which we have a great deal of information, and therefore can determine its distance.
Supernovae are excellent mileposts. Because we know their absolute brightness, we can calculate their distance from us. For example, we know the recent supernova in the Large Magellanic Cloud is only 163,000 light years away, while the supernova in this galaxy is more than 300 times further. The problem is that we need to find mileposts further in space than we can using Earth-based telescopes. Our best telescopes can only see far enough to find supernovae out to about 1 billion light years, and that's not far enough to determine how much the expanding universe is slowing down. The Space Telescope has 2 cameras that will be able to locate and study supernovae that are much further away. Of course, these cameras don't use photographic film. They use super-sensitive electronic detectors. One camera uses an array of charge-coupled devices, CCDs, to photograph objects up to 25 times fainter than is possible from the largest earthbound telescopes. It's especially good for looking at large, very distant objects, like remote clusters of galaxies. The second camera uses a very special TV tube that is so sensitive it can detect individual photons of light. This camera is excellent for observing very faint, very compact objects and extends the reach of the telescope to the greatest possible distance. With the Space Telescope's cameras, astronomers will be able to clearly locate supernovae that are up to 5 billion light years away.
By locating these much more distant mileposts, supernovae, and determining their velocities, we can then plot the deceleration rate of the universe and get a much better idea on how much the universe is slowing down.
If the expansion rate remains nearly constant, astronomers believe the universe may continue to expand forever. An endless universe might seem very appealing today, but ultimately, it would be little more than a huge, dark graveyard filled with burned-out stars. If, however, this rate of expansion slows just enough, it could mean that our cosmos is destined to collapse back on itself, that it has a finite lifespan as predicted long ago by the Mayan Indians.
All moons, all years, all days, all winds reach their completion and pass away.
One story told by the ancient Aztecs offers more hope. It describes a cycle of suns that are created and destroyed, predicting that the cosmos will bounce back out of the crunch and be reborn. With the Space Telescope as our time machine, we can look back almost to the beginning of time to see how our universe evolved. The youngest objects we can see are also some of the most mysterious, quasars. Space Telescope scientist, Dr. Margaret Burbidge.
Well, they are very fascinating and mysterious objects. On a photographic plate, they just look like ordinary stars. But when we break up their light and analyze it into its rainbow of colors, we see that they're rushing away from us at enormous speeds. And in our expanding universe, that means that they must be very, very distant, near the edge of the visible universe. Now, yet we still see them, even at these vast distances, and that tells us that they must be creating and emitting enormous amounts of energy.
To be visible from so far away, a quasar's light must be very bright, as brilliant as 200 trillion suns. And yet, quasars appear to be no larger than our solar system.
Well, we have no way to explain anything so compact being able to produce such an enormous amount of energy. And that's the real mystery of the quasars.
Much of the light reaching Earth from a quasar is ultraviolet light, light that doesn't penetrate our atmosphere. What little of a quasar's light does reach Earth shimmers because of the turbulence in our atmosphere. The Space Telescope will overcome both obstacles. It has a spectrograph that operates in both visible and ultraviolet light, and is particularly good for studying very faint objects like quasars. The spectrograph breaks light into beams according to wavelength. The beams tell us a lot about the object that produced the light, its temperature, its chemical composition, its energy state, how fast it's moving, and whether it's moving toward us or away from us. The Space Telescope also has a photometer that can measure rapid changes in light. Since it's above the atmosphere, we can use it to precisely measure the quasar's fluctuations. These two Space Telescope instruments, the spectrograph and photometer, along with the telescope's cameras, will finally put quasars within our grasp.
Well, I hope we'll be able to discover the secret of the immense energy that the quasars are producing. Might we find out something new about the laws of physics from studying the quasars? I speculate on the relationship between quasars and galaxies of stars like our own Milky Way. I sometimes wonder whether the quasars represent the birth of galaxies, and or perhaps even possibly the death of an earlier generation of galaxies. Anything might be possible.
The stars of our own galaxy have enchanted mankind for centuries. Time has dimmed neither the stars nor our fascination for them. We have learned that stars, like man, have a finite lifespan. They're born, they burn brightly for billions of years, and they die. But why do some stars burn modestly and die quietly, turning into white dwarfs that slowly cool until they no longer glow at all, while other more massive stars go out with a bang, spewing out enough matter to create several solar systems, leaving behind a super-dense cinder called a neutron star, or sometimes a black hole. Matter packed so tightly that even its own light can't escape its gravity. Our own sun is a star. How long will it burn, and how will it die? To learn more about a star's life cycle, scientists will use the Space Telescope's cameras to study other stars in the Milky Way like our sun. They'll also use information about the star's composition and temperature recorded by the telescope's second spectrograph. This spectrograph uses only ultraviolet light to produce its high-resolution spectrograms. Unlike the telescope's other spectrograph, which can study remote objects, this one is excellent for studying the objects in our universe that are closer to home. Space Telescope scientist Dr. Brad Smith.
An excellent way of studying stellar evolution is to look at globular clusters right here in our own galaxy. Globular clusters are aggregations of stars, up to several 100,000 stars, and they are all very much the same as far as their composition and age is concerned. What is different from one star to the next is its mass. So by looking individually at the stars in a globular cluster, we can see how mass determines the evolution of a star. Now, the problem with looking at globular clusters from the Earth's surface is that the poor resolution of ground-based telescopes makes all the stars fuse together. It's difficult to see them individually. But with Space Telescope and its superior resolution, we can look at the individual stars and get a better understanding of how stars live out their life cycle. We don't believe that our own star, the Sun, is massive enough to ever explode as a supernova. In all probability, it will increase in size to become a red giant star, and then shrink down to become a white dwarf. But the details of what will happen as our sun runs out of fuel are not known at this time. This is one of the things that we hope to learn with the Hubble Space Telescope.
There are many mysteries we've yet to solve in our own solar system. Though we no longer think of canals on Mars or swamps on Venus, we can't help but wonder why the cyclone of Jupiter's great red spot has raged for hundreds of years. Or what lies beneath the icy haze surrounding Uranus and Neptune. And what of Pluto, our most remote and puzzling planet? The Space Telescope will give us our first close look at Pluto and its lone moon, Charon. Astronomers expect many exciting firsts with the Space Telescope. Just as Galileo labored through the night glued to the eyepiece of his telescope, astronomers using the Space Telescope will stay glued to the modern equivalent. As a space observatory beams 1 million bits of data earthward each second. The Space Telescope will produce data of unprecedented quality, and more of it than ever before. A single observation may yield information that can take months, even years to analyze and understand. Even though the space telescope is earthbound as yet, astronomers, astrophysicists, cosmologists, and space scientists are already caught up in the exciting prospect of this new observatory taking its proper place in the heavens, and there extending their vision into previously unexplored regions of the universe.
We're really explorers, astronomers, and we're going to see wondrous things that we can't guess about. I think that's the great excitement of this, really. Certainly I'm interested in many of the things we know we're going to see, but it's the things that we don't know anything about yet, that we're not clever enough to have imagined, and I think it's going to be a very exciting time.
In the history of mankind, there have been only 2 times when our understanding of the universe has been so totally revolutionized in the period of a single human life. The first was the time of Galileo. The second is now.